Good afternoon. I'm Katherine Blundell, Gresham Professor of Astronomy. The title of my lecture today is Cosmic Vision, Unravelling Rainbows. It can be a beautiful surprise when we get to see a rainbow. I say surprise because seeing a rainbow is not something you can book for or plan. We only see a rainbow when there is a serendipitous distribution of raindrops, conveniently located to disperse the seemingly white light of sunshine into these beautiful colours. Too much cloud giving rise to those raindrops, and we don't get to see a rainbow. It sometimes seems that rainbows can follow around astronomical observatories, though I don't think this can really be the case. This is a nice example of a primary rainbow, together with a secondary rainbow displaying its colours in the opposite order to those in the primary. This photograph also shows how inside the primary rainbow it is lighter, more white, than outside of the rainbow. This arises because the raindrops that disperse sunlight actually refract the light into cones whose size depends on colour, or equivalently on wavelength, of the light. Where these cones add together, you get white light, but because they are different sizes, according to colour, according to wavelength, around the edges where the brightness is in any case enhanced, you get to see the separation of colours, their dispersion according to wavelength. This next slide actually isn't technically a rainbow. It's called a glory, and it arises via diffraction and backscattering effects when a plane is flying over cloud or mist below, and when there is also a low sun. This particular example I photographed as I was flying to South Africa. It was just after sunrise. It was just after I'd had a long, deep sleep across Africa. We were about an hour away from landing. When I woke up and looked out of the window and saw this amazing sight, I immediately grabbed my camera to try and capture the moment. This is another reminder to us that although sunlight may seem white or perhaps yellowish to us, it is in fact composed of a rich spectrum of colours. Exploring the rich spectrum of light from different stars and other objects in the night sky is the theme of today's lecture. But first, I want us to think about colour. It perhaps won't come as a surprise to think of colour as carrying information. Colour has, of course, long played a role in terms of symbolism. Purple has long been associated with special things, such as royalty or bishops. But in recent days, purple has been discussed as being the colour of bipartisan unity, combining as it does red and blue. Besides symbolism, important though that is, colour tells us a lot. This is particularly important in astronomy when we can never handle or poke or prod what we are studying. The kind of information from colour that I'm talking about isn't the kind of information that depends on the eye of the beholder or the cultural predisposition that the observer may or may not have. Colour perception and understanding the representation of colour are not entirely straightforward. We know that digital images are represented by pixels, small squares of single colours across that individual pixel, which collectively together give us a sense of the colour distribution of whatever it is that is being photographed. Human eyes are very good at interpreting over a mix of data, be it a mix of colours or a mix of pixels. Sodium street lamps fill cities with distinct orange light. It's a very specific colour, and it arises from just two very specific wavelengths of light wave. It's an orange colour because sodium atoms, which is what the vapour in these street lamps is composed of, have a particular transition between fixed energy levels, which equates to orange light. When we see that precise colour of orange, we can infer that there is sodium vapour in the street light. But when we photograph that street light and then zoom in on that photograph on a computer screen, we can see that the pixels in the image are themselves composed of pixels in the monitor, which are themselves represented by varying amounts of red or green or blue light. Fortunately, human beings, even though they have only 3 colour receptors, approximately corresponding to red and green and blue, are nonetheless very good at interpreting the relative amounts of red and green and blue, and interpolating and interpreting to a much richer spectrum of colours than our 3 colour receptors might at first suggest. In astrophotography, the way that we make a colour image is to combine light from the red and the green and the blue parts of the spectrum that come from that object. When light is collected by the telescope, it passes through a red filter. In other words, a filter that allows the throughput of red light, but blocks the passage of green or blue light. So what we're looking at here is an image of only the light in the red part of the spectrum from this particular field of view, the Trifid Nebula, Messier 20. All the light that we see on this image in front of us is red light. All the light from the green part of the spectrum is blocked, all the light from the blue part of the spectrum is blocked. But then we make successive observations with a green filter, blocking the red light and blocking the blue light and only allowing the green to pass. And then finally, our third image is going to be an image made with a blue filter that only allows the blue light to pass. And I hope you get a sense that you get slightly different distributions of light in each of these 3 channels. If I now colour up the red light, the green light, and the blue light, and then add those 3 images together, the resultant image is a beautiful multicolour image of this amazing nebula, the Trifid Nebula. So white light that we see is the combination of light of different colours. You can fool the human eye into thinking that there is a full spectrum of light at all wavelengths just by taking the light of 3 specific colours, red, green and blue. The relative ratios of the light in the 3 different colour receptors in our eyes are sensitively interpreted by our human brains to fill in the whole gamut of colour. This beautiful nebula shows us differently coloured gases. The red gas that you can see here is predominantly hydrogen gas, whereas the blue light is a combination of light from hot blue stars together with the light from those blue young stars reflected off ambient gas further out. And so by combining these 3 channels, we get a beautiful image of the Trifid Nebula. This one was made by my colleague, Stephen Lee. Now let's talk about something a bit more everyday and closer to home. When we put the lights out at bedtime tonight, we expect the room will go dark. And as far as our human eyes are concerned, it is dark, it will be dark, at least as far as the visible spectrum to which our eyes are sensitive is concerned. But actually, it should be remarkable that it's dark as far as our human eyes are concerned. And that's because all objects glow even when they are not irradiated. The colour or the waveband at which they radiate depends critically on the temperature of the object. Which part of the spectrum an object glows at, i.e. what colour it is at, depends very much on its temperature. And of course, this is very familiar to blacksmiths. As a blacksmith is heating up a piece of steel to bend it into a horseshoe or a railing, if the blacksmith sees the metal to be a muted red colour, then that will be a sign that the temperature of the metal is about 600 degrees. Hotter still, when the metal is bright red, that will be because it is at a temperature of 800 degrees. Adding yet more heat energy and raising the temperature further, when orange light is seen, the steel will be at 900 degrees, and so on, until we get to white light at 1300 degrees. Let's see if we can understand why we should have that sequence of colour, from red to orange to yellow to white. That is not the pattern of colours in the rainbow, or is it? So colour gives us temperature, and this is understood most simply in terms of a device, a conceptual device in thermodynamics called a black body. A black body is an object that doesn't absorb or emit light preferentially at any one particular colour or waveband compared with any other particular colour or waveband. If a black body is at a particular temperature, then you can predict exactly what spectral shape, what rainbow shape it will have as a function of colour or of wavelength, totally in terms of its temperature. So the plot that I'm showing here has on the bottom axis colour or frequency of light, and on the vertical axis the intensity of light, how bright a particular object will be radiating at that colour. Now the grey panel indicates the approximate range at which human eyes are sensitive to. So for the very cold object at 20 degrees over on the left, we can see that there is essentially zero radiation at the visible wavelength. It's all right down in the infrared at very long wavelengths, at very low frequencies. But if the temperature of something, such as a piece of hot steel, is up in temperature ranges like 600 or 800, then that will just start to creep into the visible spectrum as red or orange light. If it's hotter still, we'll start to see yellow light. By the time it's up at about 1300 degrees, then we're seeing light right across the visible spectrum, which our human eyes will sum up to see as white light. Hence, we will see the steel to be white hot. And so it's worth keeping in mind that objects which glow in terms of heat are also glowing in terms of light. But it's only at very, very high temperatures that you will actually have a sense of light which is being radiated in accordance with the temperature of the object. Normally, the things that we see around us, we see light from them, we see the shape they are, we see the structure that they have, the colour that they are, because of how much light they're absorbing. This blue dress absorbs red light, and so it isn't seen as red, it's seen as blue. That light is nothing to do with the temperature of the object. And it's the same with stars. I'm now going to show you an image of a cluster of stars, perhaps surprisingly, an out of focus cluster of stars. Here is the in focus image, here is the out of focus image. And I'm showing you the out of focus image because it's that much easier to determine from the spread out unfocused images of those stars, the fact that they can all be very different colours. There are blue ones, there are white ones, there are yellow ones. And the yellow ones are the ones that are cooler. The blue stars are the ones that are hotter. They've got much more energy being radiated at the high frequency, short wavelength, blue part of the spectrum than the cooler stars have. And so that's why stars can appear to be different colours in the night sky. It is simply because of their temperatures. Cooler ones appear yellow, even cooler ones appear red. hotter ones appear white, even hotter ones appear blue. So now let's return to what colour is sunlight. Well, if we take a spectrum of the sun, then it looks rainbow-like, as you would expect, because a rainbow is the dispersed light from the sun. Where this image differs from a rainbow is that instead of the dispersing element being raindrops, the dispersing element is a grating in a spectrograph. The sun radiates light at all these different wavelengths or colours, blue, green, orange, red, and so on. And that combination of colours is perceived by our eyes, not that we ever look at the sun, to be sort of yellowish white. The sun also radiates in the UV, which is why we can get sunburn, and also in the X-rays, and also in the infrared, and also in the radio. But the sum of the different colours radiated in the optical band are what lead us to conclude that sunlight is yellowish white. You may notice that this particular spectrum, dispersed as it is via a grating in a spectrograph and not raindrops in the sky, shows some very sharp vertical dark lines. The first person to spot this was Joseph von Fraunhofer, the German physicist, who made one of the first spectrographs out of some simple little prisms. And he investigated these dark lines in quite some detail. I'm showing here a zoom in of the so-called Fraunhofer D lines. These two lines occur at exactly the wavelengths or specific colours that the orange light from sodium street lamps radiate at. This turns out to be an exact fingerprint of sodium atoms, or at least of the transitions between different electronic states of those atoms. The exact wavelengths corresponding to the specific electronic transitions within those atoms give a very precise fingerprint or signature of that particular element or chemical species. It can be very interesting to look at the night sky through a filter that only passes sodium light and blocks out all other light. So all of green, all of blue, almost all of red, but just passing through the orange lines corresponding to that little sodium doublet that I showed you in the previous slides. It may seem like a rather foolhardy thing to do to attempt to observe the night sky in sodium light, but really that statement is only true for those of us who live nearby lots of sodium street lamps, which colour our night skies that rather annoying orange colour and which pollutes our attempts at astronomical observations. Well, an amateur astronomer in Italy did observe the night sky through a sodium filter. And this is what he observed. This is actually an image of the planet Mercury when imaged through a sodium filter. It reveals a tale of the kind associated with comets, such as that of Comet Neowise, which appeared in our skies last July. I showed some images of Comet Neowise to you in my second lecture of this academic year, Cosmic Vision, Attentive Eyes. The remarkable thing is that Mercury has a tail which glows in sodium. Mercury has an atmosphere which contains a lot of sodium, and it's the planet that is nearest to the sun, so it has a much more ferocious experience of the sunshine and the sun heat that come away from our nearest star. And so some of that atmosphere is blown away into a tail. And it's been beautifully imaged here by Andrea Alessandrini. The tail itself is something like 24 million kilometers long. And this exposure only took 7.5 minutes to create. So it's not an especially faint tail either, but you can only easily see it in sodium light. This is a picture of Andrea here with the relatively small telescope and the fairly standard DSLR camera with which he made this rather wonderful observation. Another important way in which colour can give us information is that it can reveal the identities of the elements that we have present in different gas and in different plasma. This next slide shows dispersed in wavelength or in colour the particular emission lines that you get from hot gas comprised of hydrogen on the top row, sodium on the second row, you can see those two D lines showing up again, helium on the third row, neon on the fourth row. When we look at a neon sign and see something that is truly neon gas glowing, it seems to our human eyes to have a sort of pinky, orangey, red kind of colour. And that arises because of the way that our human eyes interpret and interpolate over the emission lines in the yellow, orange, red part of the spectrum that you can see in the fourth row here. Mercury has a different distribution of lines all over the spectrum that are different again. And so if we can disperse light from different gas clouds, from different nebulae, we can absolutely identify which chemical elements are present, which ones we have on the periodic table. It's interesting to reflect that when we see a meteor or a shooting star in the night sky, sometimes these can be associated with very distinctive colours. I've seen quite a few green ones. And when you see green light coming from a meteor or a meteorite, such as this one I'm holding up here, that green light can be a signature of copper or of iron. This particular example was discovered in the garden of my great-grandfather-in-law quite a long time ago now, and I'm sure it was associated with a very bright streak of light through the night sky before it landed in that Warwickshire garden. So across all of the periodic table of the elements then, for each distinct element, there would be a distinct spectrum of emission lines when you have a hot gaseous form of each particular element. This particular arrangement of the periodic table is arranged according to the electronic structure of the atoms. The version of the periodic table that I'm showing to you now is a somewhat different arrangement. And this representation communicates the relative abundance of the different types of elements here on planet Earth. You can see that there are roughly equal quantities of hydrogen, of carbon, and of oxygen. If we were to do this version of the periodic table for different stars, we would see that it's very different from the representation shown here for planet Earth. Most stars are predominantly hydrogen. Of course, many stars have different elements still because they've evolved differently and they've undergone different nucleosynthetic processes. If we look at different stars with a spectrograph, they have different spectra, arising partly from their different temperatures, but also from their different chemical compositions. Stars that are made out of gas, that is itself the ejector of a previous explosion, will be much more enriched with elements from further down the periodic table than just hydrogen and helium, compared with stars that formed from pristine gas much earlier in the history of the universe. I'm now going to show you an image of some stars, which is actually a very familiar constellation. At least I hope it will be familiar to you when I put rings over each of the most prominent stars in the constellation. This is, of course, Orion. And what's different about this image is that each image of a star, which would normally be point-like on an astronomical image, is itself resolved into a rainbow, a spectrum of different colours. Let's zoom in and take a closer look at Betelgeuse. Betelgeuse has quite a lot of red light. It doesn't just emit red light, however. Look at a dispersed version of its colour. Although it can look red in the night sky, when we look up at the constellation of Orion with our eyes or with a pair of binoculars, it doesn't just emit red light. When we look over at Rigel in the diametrically opposite corner in Orion, however, Rigel has a different spectral shape, a different rainbow from that of Betelgeuse. It's still radiating red light for sure, but there's now a lot more violet light. And indeed, when we look up at Orion, Rigel seems to be much more bluey white than Betelgeuse, which is reddy orange. And that is simply because of their different temperatures. We can understand this in terms of the black body spectra that I showed you earlier. Betelgeuse is a much cooler star than Rigel. We think Betelgeuse's temperature is something like 3,600 Kelvin. The difference between Kelvin and Celsius is only 273 degrees. So when you're getting to these really high temperatures in the thousands, it doesn't matter a whole lot whether you're talking Celsius or Kelvin. But anyway, Betelgeuse is something like 3,600 Kelvin. And so we do see that there's rather more red light in Betelgeuse than blue light, and so it appears reddish to our eyes. Whereas Rigel, being rather hotter, has light all across the visible spectrum in approximately equal quantities. So it looks white or whitish blue because of its high temperature of 12,000 Kelvin relative to Betelgeuse. The sun is somewhere in between, as I said, giving us that yellowish whitish light. Back to this spectrally dispersed image of Orion. So these then are the main stars, but I want to focus now on the spectrum not of the stars, but of the nebula M42, Messier 42, shown in Orion's belt. I've shown you a zoom in of this particular nebula previously. Here is a beautiful image of Messier 42 made by my colleague Stephen Lee. The red light there is actually radiating as a result of excited hydrogen gas. The greenish whitish light is radiating because it is illuminated oxygen. And so if that's the case from this zoom in, we ought to expect that when we take a spectrum, a rainbow of Messier 42 in an integrated way of the whole nebula, that it would look a little different from the spectra of stars. And so it is. When I zoom in to the spectrum of M42 itself, I hope you can make out that there are two bright emission lines, two bright peaks in its rainbow. One of these is hydrogen, one of these is oxygen, exactly consistent with the gas we know to be radiating in that nebula. So when we understand which emission lines correspond to which wavelengths, i.e. to which colours, then we can diagnose which elements from the periodic table are present in a particular phenomenon in the night sky. So how do we go about studying these in more detail? Well, as I've already indicated, the human eye is a bit too good at interpreting and interpolating from just its three colour receptors of red, green and blue into differential colours that may or may not be present. To actually carry out such studies of the spectra or rainbows of different stars in a scientifically rigorous and measurably repeatable way, we need to use a spectrograph. So a spectrograph disperses light from stars in much the same way that raindrops disperse light from the sun. But the dispersing element in this case is a piece of glass, or what looks like a piece of glass. It's actually a grating which disperses the light according to colour, according to wavelength. Coloured information comes in It's a coloured signal that comes in, all the light from the entire spectrum, that's fed into the spectrograph, it's dispersed by this grating element here, and then it's directed onto a monochrome camera, the type of camera I was talking about earlier, that just responds to the intensity of the incident light and captures how faint certain regions are and how bright other regions are. We can measurably quantify which wavelengths we get which intensities of light through the spectrograph. And that's because the dispersing element disperses the light according to different wavelengths into different positions along the detector. Wavelength of the spectrum goes from shorter wavelengths in the bottom left to longer wavelengths, redder colours, in the top right. This could equally well be labelled with frequency going from lower frequencies in the top right to higher frequencies in the bottom left. If we know and understand the positions of all those bright points on the spectrum, they are emission lines from our calibration lamps, we can absolutely calibrate the positions of different spectral features in our rainbow, in our spectrum, and understand exactly what they are. And we can do this because we know that our calibration lamps contain thorium krypton elements, which give rise to these emission lines at very specific wavelengths. We match the positions of the different points of light to the wavelengths where they occur, as measured in laboratories. And so we can precisely calibrate the emission lines that we get collected by our telescopes, pass through our spectrographs, precisely against this referenced spectrum. Why is that important? It's important because another big component of the information that colour brings us are things like speed, dynamical information, acceleration, all that kind of thing. Colour information gives us speed when combined with something well known to physicists called the Doppler effect. The Doppler effect is the effect whereby whatever colour something appears to be radiating at, it will radiate at longer wavelengths, redder colours, if it is moving away from us. The street lamp that appears to us to be orange when it's stationary on our pavement would, if it were propelled away from us at great speed, appear to be emitting red light. This would be a consequence of what is known as a red shift. This is completely analogous to what happens when an ambulance is hurtling towards us. Its siren is heard to be at a higher pitch, at shorter wavelengths, in contrast to when the ambulance is moving away from us. We hear the siren then to be at a lower pitch, at longer wavelengths. The Doppler effect applies equally well whether you're talking about sound waves for a siren or light waves from a distant star. Another important component of information that colour brings to us, besides speed, is also distance. The Doppler effect means that it's pretty easy to measure the speed at which a galaxy is moving away from us or towards us, in the case of our neighbour, the Andromeda galaxy. What we do is to measure a spectrum, and it will have emission lines corresponding to what types of stars are present in the galaxy. We work out how displaced they are towards the red end of the spectrum, and by measuring that redshift, it is very straightforward to calculate the speed at which the galaxy is receding from us, its recession speed, and that relates directly to the distance the galaxy is away from us. Slipher and Hubble worked on this over a century ago. They found an important relation which we now know as Hubble's law, which is that the further away a galaxy is from us, the faster it is receding from us. This is something that I discussed in quite a bit of detail in my second Gresham lecture, entitled Cosmic Concepts Frozen in Time. And so using these techniques, the Doppler effect, spectroscopic observations of galaxies, it was possible for the most distant known galaxy to be observed and to have its recession velocity determined. So this was work done by Ursch and by Brammer, looking at a distant galaxy that we now call GNZ11. The name derives from its location in the sky. It's a location called Goods North. It's in Ursa Major. And the Z11 refers to the fact its redshift is 11.09. And what that means is that the look back time to the galaxy is well over 13 billion years because it has a redshift of 11. We believe that the light from this galaxy that we now observed left this galaxy a mere 400 million years after the Big Bang. And that is a record holder. It's a remarkable thing that galaxy formation can happen in such a relatively short time as 400 million years following the Big Bang. But you'll see that this galaxy is very irregular in its form. It's not one of these beautiful spiral galaxies, which takes rather longer to form that beautiful shape. So the Doppler effect is helpful to us not just in terms of cosmology and measuring the distances to galaxies far across the other side of the observable universe. It's also important and useful for determining the dynamics of rapidly evolving objects in our galaxy. This is a spectrum that I'm showing to you, observed of a famous microquasar known as SS433 in our galaxy. This particular object has at its heart a black hole, as I described to you in my third Gresham lecture, Cosmic Concepts, the End of Matter. This particular spectrum has three very prominent emission lines. The one colour-coded here, green, arises from hydrogen gas, and it's referred to in the field as the stationary hydrogen alpha line. It's called stationary, but it's nothing of the sort. It wiggles around in a way that arises from the orbits of material orbiting around the black hole system, and also the matter as it is sucked in towards the black hole, as I described in that lecture on the end of matter. But there are two other prominent emission lines. One is one towards the bluer end of this particular spectrum. This blue shifted H alpha line arises from hydrogen gas, which is radiating light in its own rest frame at the normal sort of frequency to that represented by the green line at 6563 angstroms, but that gas is moving towards Earth, shooting towards it at rapid speeds. There's also a corresponding redshifted line, corresponding to light radiated from hydrogen gas, which is hurtling away from Earth. And this is one of the reasons why it's such a joy to study this particular microquasar. Every time you look at it, it changes, it looks different. And that's because the redshifting and the blue shifting hydrogen gas arise from packets of plasma that are squirted out from the vicinity of the black hole about an axis, a direction, which changes systematically and steadily with time, which is why we see it gradually change its redshifting and its blue shifting. Much more of that, as I say, in my lecture on the end of matter. But colour gives us information that reveals dynamics. And now I want to focus on how time-resolved spectroscopy can also help with elucidating different dynamical situations. The two different dynamical situations that I'm representing, one in a series of red spectra and one in a series of blue spectra, are illustrated here. They may at first seem the same, but if you wind up the spectral resolution to show it in more detail, you can see that actually they are a very different picture, and that's because they arise from very different dynamics. On the left, you've got a situation whereby two emission lines are rock steady in wavelength, but they go up and down with intensity throughout time. And this arises because of a ring of gas that's constantly rotating around a central mass, but the intensity of those lines changes as a beacon, something like a lighthouse beam, illuminates that ring of gas in turn. It's a completely different dynamical situation from what we have on the right, shown here in blue. And that's when you've got two stars in orbit around one another, whose emission lines go backwards and forwards according to the Doppler effect. Time-lapse spectroscopy or time-resolved spectroscopy can make all the difference between being able to understand which dynamical situation you've got. And so time-lapse spectroscopy, such as that performed by the global JetWatch observatories, is an extremely powerful tool in the toolkit as we seek to understand the dynamic, evolving universe. But now let's come even closer to home. In my last lecture before Christmas, the one entitled Cosmic Vision, Witnessing Fireworks, I spoke to you about the fact that in December, just before Christmas, on December the 21st, there would be a great conjunction of Jupiter and Saturn. Fortunately, at my India School observatory that's part of the Global JetWatch network, we had clear skies. And we were able to observe it on the 20th of December, on the 21st of December, and on the 22nd of December. The 21st of December was when they had their closest approach. Being able to observe before and during and after gave us a sense of how rapidly they were moving through the sky with respect to one another. This third and final image, taken on the 22nd of December, shows 5 moons in total, 4 Galilean moons in orbit around Jupiter, and 1 moon, Titan, in orbit around Saturn. Both of these planets have many more moons in orbit around them, as I've described in previous lectures, but these were clearly visible in the very short exposures that we took when we observed Jupiter and Saturn just before Christmas. These observations had to be made just after sunset because Jupiter and Saturn themselves were about to set. It's fun to consider what a rainbow of Jupiter would look like, what a spectrum of Jupiter would look like. And so I'm now showing you what a two-dimensional spectrum of the planet Jupiter looks like. So the spectrum that's shown here is substantially elongated up-down as it samples data from all across the equator of Jupiter, shown there on the right with its stripes being vertical for this particular illustration. Wavelength increases from left to right. And you may be able to see that this spectrum is characterized by dark lines. If I zoom in, then it is perhaps a little bit clearer that some of these lines are vertical. Those actually arise because of absorption by fairly cold gases in our own atmosphere. But there are also slanting lines, and these arise from absorption of gases in Jupiter's own atmosphere. The part of the spectrum that's shown indicated by a blue arrow arises from gas which is absorbing the light that's coming from the sun but is also moving towards us. That's why it's blue shifted. The part of the spectrum that's indicated by the red arrow is again absorbing light from the sun, but that bit of Jupiter is moving away from us because Jupiter is spinning on its axis. The equator is constantly rotating around as the entirety of Jupiter orbits around its axis. And so from this, it's possible to derive a spectrum at all these different heights across this broad 2D spectrum, and to give us information about the speed at which different bits of gas all across Jupiter's equator are moving with respect to Earth. And you can see that there's a composite of a number of different spectra there, all from different sampling points around Jupiter's equator. There are two extremes, all the way from the blue shifted gas moving towards Earth to the red shifted gas moving away from Earth. And from these observations, it's possible to extract the speed at which Jupiter is rotating, and then to derive the period of rotation or the spin period of Jupiter. And it turns out to be about 10 hours. So Jupiter spins on its axis in about half the time, or less than half the time, that it takes Earth to spin on its axis, which of course takes 24 hours. You can verify this for yourself if you have a telescope that's able to resolve the giant red spot of Jupiter. You can take successive observations of how long it takes for the giant red spot to track across Jupiter, and then work out how long it would take to go all the way round. And I'm sure you'll find out that it's about 10 hours for the spin period of Jupiter. 14 hours quicker than the spin period of planet Earth. I do hope that you've enjoyed learning about the different kinds of information that we can learn from very many different astronomical objects if we unravel their rainbows. Thank you. Goodbye.